In the second photograph, the wing is mounted at the bottom of the fuselage. This is called a low wing configuration. Okay. Similarly, in this next slide, you can see that the wing could also be mounted in the middle of the fuselage, somewhere between the top and the bottom, right? So there are three photos here. On the top photo, the wing is mounted on top of the fuselage. In the middle photo, the wing is mounted in the middle of the fuselage. And in the lowest photo, the wing is mounted at the bottom of the fuselage. Okay. So there must be a reason why we have these options, and there must be a reason why the wing must be mounted on a certain height. Okay, and this will affect the aircraft's performance. And in the second figure, the wing is bent downward. Okay, so this is called a anhedral wing. The top one is called the dihedral wing, right? So we will be talking about that as well, and we'll try to understand how that affects the stability of the aircraft. Okay. Similarly, let's look at this third slide. So in the first figure, the wing is swept backward. In the middle figure, there is no sweep. It's called a straight wing. Okay. And in the third figure, the wing is swept forward. And again, this has to do with the stability characteristics of the aircraft. So in this slide now, I'm only showing the tail section. And here also you can see some differences, right? So for example, in this figure in which we have three tail sections being shown, the horizontal fin is attached to the end of the fuselage. Okay, but in the middle figure, the horizontal fin is attached to the vertical fin, right, to the top of the vertical fin. So why would that be the case? Like, why in some aircrafts these horizontal wing fins are attached to the fuselage, whereas in other aircrafts they are attached to the top of the vertical fin? Okay, so these are the type of things that will be covered in this course. We have all heard the word stability. This word is not new to us. Let's say we have a ball and there is a ball at the bottom of the ball. Now this could be a stable situation, right? The ball is not going anywhere, it is not moving, and it is staying where it is. Now instead of a ball, let's say we have a curved surface, and on top of this curved surface we have balanced a ball, and it is staying there, okay, by itself. All the forces are balanced, it is not moving anywhere. This is also an example of a stable condition, but it is not equally stable as the first example. Similarly, we could have the ball on a flat surface. Now, from our intuition, we have a hunch that all these three examples cannot represent the same amount of stability, right? It cannot be the same in terms of our natural perception of stability. Somehow they feel different. Now, how are they different? Let's try to investigate our own thoughts. If I move this ball here and then I release it, what will happen? It will come to the bottom and it may overshoot, and it may again come to the bottom of the bowl and then overshoot, and this process may continue, right? So the tendency of this ball, when it is displaced from the bottom of the bowl, is to come back to its original state. Now in the second example, if I displace this ball, what will happen? It will just move further away from its initial location, right? So it will, if I displace it to this position and I release it, it will continue to roll downward. It will move further and further away from the initial location. Now in the third case, I push this ball, I bring it here, and then I leave it, it will stay in the new location. Okay. Now, here we need to be aware of a few things to get a very clear comprehension of this three different situations. Number one, this initial condition in these three cases, this is known as the equilibrium condition. So this is an equilibrium condition. This is an equilibrium condition. And this is an equilibrium condition. In fact, it is the equilibrium condition in which all the forces are balanced, right? So when you say that all the forces are balanced, you guys say that that is being stable. That is fine. But to be more accurate, that is actually an equilibrium condition. Equilibrium means there is no change. Okay, things are staying where they are. Now, when you displace this object from the equilibrium condition, how does it behave? That will determine its stability characteristics. In the first example, you displace the ball from its equilibrium, it tries to come back to the equilibrium condition. Okay, so this is an example of a statically stable case. This is statically stable. In the second example, you push this ball and it goes more and more away from the equilibrium condition. This is an example of statically unstable case. And then in the third example, you push the ball to a new location and it stays there. This is an example of a neutrally stable state. Okay, so this type of behavior is called neutral stability. And these three different types of stability that I have listed they are all three different types of static stability. So I'm saying static stability. I've added an adjective to the word stability. That is because there are two types of stability. Okay, we can categorize stability into two types. One is static stability. Another is dynamic stability. So what is the difference? Now, in the case of static stability, you are only concerned with the initial tendency of the system. So you disturb the system, and what is its initial tendency? Does it want to come back? If it wants to come back to equilibrium, that's a statically stable system. For instance, this is an example of a statically stable system because you disturb it, you move the ball slightly away from its equilibrium position, it has the initial tendency to come back to its equilibrium. So it's like a person, who leaves home and goes to another country, and the initial tendency of this person is to want to come back to the home country. So this is an example of being statically stable. Okay. Now another possibility is you displace the object or you change the system, and it just continues to go further and further away from its equilibrium. So for example, this is like a person who goes to another country and just forgets the home country, right? So just continues to get more and more disconnected. So this is the example of a statically unstable system. All right. And the third example is you make a change to the system and it stays in the new condition. Okay, so this way there are three types of static stability. Now, what is dynamic stability? Dynamic stability is more concerned with the time history of a system after it is disturbed from the initial state. For example, let's take this statically stable case. Now we can imagine several ways in which this ball will try to come back to the equilibrium. When you push it to its new location and release it, it may roll and then it will come to the equilibrium and just stay there. Okay, so there is no any oscillation. This is one possibility. This can happen if the friction is very high. Another possibility is it will roll and then it will overshoot. So it will oscillate and then it will finally come to the equilibrium. Now, another possibility is for some reason it will come to equilibrium, it will overshoot and it will oscillate, and the amplitude of this oscillation grows more and more and more. So in all these three cases, the system is statically stable in the same way, but it has different dynamic stability characteristics. Okay, because dynamic stability is concerned with the entire time history of the system, of the behavior of the system once it is perturbed, whereas static stability is only concerned with the initial tendency. To note the main difference between the static stability and dynamic stability, let's say that static stability is concerned with the initial tendency of a system to return to its equilibrium position. Whereas now dynamic stability, it is more concerned with the time history. Right, it is concerned with the time history of motion of the system after it is disturbed. So the important difference is, when you are trying to characterize the dynamic stability, you have to look at how things are changing with respect to time. Whereas when you are trying to characterize the static stability, you don't care about how things are changing with respect to time. You only care about how things are changing initially. You only care about the response at the initial time. So this is important and relevant for aircraft motion, because when an aircraft is flying, it can also get disturbed. It is flying under certain conditions. It is flying at a certain velocity, at some angle of attack, at some altitude, and then because of some changes in the atmospheric condition or because of pilot behavior, the aircraft can get perturbed or disturbed from its equilibrium state. Okay. Now, there are two questions after this. One, does this aircraft have the tendency to come back to the equilibrium? We would like it to come back to the equilibrium, right? Because you don't want to be flying in an aircraft which starts shaking because of turbulence and then just continues to shake and shake more and more, right? You want maybe for it to come back to the equilibrium state as quickly as possible, for example, right? So this is one thing that you want to know, its initial tendency. Another is, how does it come back to the equilibrium state after it is disturbed? All right, so in some of the things that I just said, there are two things you should note. First of all, that this type of disturbance can be created by atmospheric phenomenon or pilot's action, right? The aircraft may be disturbed from its equilibrium state by two factors, right? By atmospheric phenomena, that means, for example, a gust of air, atmospheric phenomena, or pilot's action. The pilot may do something which may also try to change the state from the equilibrium state to some new state. Okay. And given this change, the vehicle may be statically stable, dynamically stable, or both. Right. I'm going to now give some examples of the different types of dynamic stability. Okay, I already gave an analogy for the static stability. Now just some graphical examples of dynamic stability. Okay, this is So let's consider the plot of displacement. As a function of time. Let's say you displace the aircraft from its equilibrium position. So you can imagine that its angle of attack has been slightly changed, or its altitude has been slightly changed. Okay, so this displacement could mean a change in any variable. Then let's say this is the initial displacement. Now we want this displacement to go back to 0, right, so that the aircraft comes back to the equilibrium. So it can come back to equilibrium by following this plot. So let's say it comes back to equilibrium after some time t, and it does that just without any oscillation, like you displace it. So let's say the aircraft is flying at some angle of attack, and then a gust of wind came and hit the fuselage and the wings, and now the aircraft is slightly rotated, slightly pitched up by an additional angle of attack. So there is a change in angle of attack by delta alpha. Okay, so this displacement is your delta alpha, for instance. Now how will this rotated fuselage, this rotated aircraft, will come back to its original orientation? Let's say it just comes back slowly over time to the angle of attack that it started with, that it was originally flying at. Okay, so this sort of a displacement behavior as a function of time is called subsidence. Now these are just names, okay? It's nothing special. It's just a way to distinguish the different types of behaviors that we may observe depending on the design of the aircraft. So another possibility for displacement versus time is, let's imagine that the gust of wind came and it changed the angle of attack, it increased the angle of attack. Instead of coming back to the original angle of attack, instead of again start to pitch down, the aircraft could just continue to pitch more and more up. Then in that case, the displacement versus time plot will look like this. So the angle of attack changed by delta alpha, and over time the aircraft just continued to pitch more and more up. Obviously we may not want that to happen, okay, but one may end up designing an aircraft which behaves like this. Then this sort of a displacement versus time behavior is known as divergence. And sometimes it may be desirable to have this type of characteristics. Like, for example, you are developing a military aircraft for air combat, then maybe you want to be able to maneuver it in any way you like. So instead of the gust of wind, imagine that the change is brought by the pilot, right? Because we said there could be two factors, atmospheric phenomenon and pilot's action. So the pilot wants to change the angle of attack, and the aircraft just immediately responds. It doesn't want to come back to the equilibrium at all. And this may be desirable for an aircraft in which you want to have very easily maneuverable characteristics. Okay, but again, in some other types of aircrafts, you may want to avoid this. So you have to be aware of this sort of a displacement versus time behavior. Now, another possibility is, let's say this gust of wind comes and it hits the fuselage, the wing, and it changes the angle of attack by delta alpha, and the aircraft just stays at this new angle of attack. Okay, then in that case, the displacement versus time plot will look like this. So you displace the aircraft by delta alpha, and it continues to stay at delta alpha. So this is neutral stability. So now in these three examples that I described, this is an example of a system which is dynamically stable. And this is an example of a system which is not dynamically stable, right? It is dynamically unstable. Now, for a system to come back to equilibrium like this, for for the angle of attack to come back to its original value, it needs to have something called positive damping. Okay, so this system has positive damping. So what positive damping does is it dissipates the extra energy that the system obtains. Like, so the wind hits this aircraft, so its energy increases, but once the energy is dissipated, once it is just lost, then the aircraft will come back to its original angle of attack. So a dynamically stable system is characterized by positive damping, and these damping ratios will be one of the variables that we will be interested in calculating later on in the course. Whereas a dynamically unstable system is characterized by negative damping. So in this type of system, what happens is you give it some energy and that just grows. So the angle of attack increased by delta alpha and it just continues to increase. Okay, so in such system, if you have ended up designing such a system which is characterized by negative damping, then you may want to introduce some artificial damping into the system so that it can be brought back into equilibrium. Okay, so again, these things will be more important when we actually write some equations and we calculate the damping ratios. So their values being positive or negative is going to imply whether the system is dynamically stable or not. Now, when the angle of attack changes by delta alpha, this could also lead to some oscillations. For example, although eventually the aircraft may come back to its original angle of attack, it may not necessarily do it monotonically, right? So it may not just slowly decrease and come to delta alpha equals to 0. The angle of attack may also start to oscillate, right? So you could get this type of a behavior, for example. This sort of a displacement versus time behavior is called damped oscillation. So in this case, as time passes, okay, the aircraft is going to pitch up and down, right? So there is going to be some oscillations, and then eventually it will come back to its equilibrium state. Now, another possibility is the wind comes, it introduces some delta alpha, so there is a displacement in the value of angle of attack, and this just sets off an oscillation which is undamped. Okay, so you may just continue to have oscillation over time. So it just starts to oscillate and maintains the same amplitude, and this continues forever. So this is an example of undamped oscillation. And the third possibility is, again, we get oscillations, but these oscillations continue to grow bigger and bigger. So you have initial displacement of delta alpha, and it just continues to grow bigger and bigger. So this is an example of divergent oscillation. So in this way, you can see that there could be various types of dynamic stability. Okay, so I think we covered 6 different types. Okay, so 3 for the cases in which there is oscillation, and 3 for the cases in which there are no oscillations. So far we have only become aware about the different ways an aircraft may behave once it is disturbed from its equilibrium state. Okay, we have talked about its initial tendency, and this initial tendency characterizes the static stability, and we also talked about the time history of the system after it is disturbed, and this time history is related to the dynamic stability. Okay, so I have only introduced the concepts. Now let's go a little deeper. We will now focus only on static stability, and we will now try to become more quantitative about this. And I'm going to start this with an example. Okay. Imagine CM versus alpha. So this is like your airfoil data. As you may recall from previous courses, you have studied about airfoil data, which has included lift coefficient versus angle of attack, drag coefficient versus angle of attack, moment coefficient versus angle of attack. I'm only going to focus on the moment coefficient as a function of angle of attack. Now let's say there are two airplanes that we are going to compare. Airplane 1 has CM versus alpha, which looks like this. So this straight line represents CM versus alpha for airplane 1. And let's imagine that there is another aircraft for which CM versus alpha has a positive slope. So this is airplane 2. So this point, what is the value of CM at this point? CM equals to, so here is my aircraft, and it is flying in the horizontal direction, let's say towards the left. Okay, so let's measure the angle of attack. Yeah, let's give it a label. Let's call it point B. So this is my alpha B. So at this angle of attack, there is no resultant moment, means there is no resultant turning force on the aircraft. The aircraft is not, it will not turn, it will just stay at this angle of attack. Okay, so this condition in which CM equals to 0, net moment equals to 0, this is the equilibrium point, right? Is the CM equals to 0, that is at B is the equilibrium point. And there is another name for it, and you have to learn this name. It's also called the trim point. So when the aircraft is trimmed, that means it is in equilibrium. It's not going to start changing its angle of attack or changing its altitude, things like that. Okay, so it will maintain its state. So trim point, you have to remember this. Trimmed condition means equilibrium condition. Now let's imagine that suddenly, because of something in the air, wind came or something happened, and it hit the aircraft, and its angle of attack slightly increased. So the new angle of attack is represented by C. Okay, so this new angle is the alpha C. Now let's compare what's going to happen in airplane 1 versus airplane 2. Let's see what will happen in airplane 1. Okay, so airplane 1 means now at this new angle of attack, alpha C, so when the angle of attack is now alpha C, the moment coefficient is something negative, right? So negative. What does negative moment coefficient mean? Negative moment coefficient means the moment which is trying to rotate the aircraft downward. So it is trying to decrease the pitch angle. Okay, so if this is the aircraft, pitch up is positive moment. Pitch down is negative moment. So when the angle of attack is alpha C, we get a negative moment, means airplane 1 will experience a force which will try to rotate it downward. So if this airplane that I've sketched here, if this is airplane 1, then when the angle of attack is alpha c, it will experience a moment which will be negative. So it will try to make the angle of attack back to alpha b. So this is a statically stable aircraft. Now, if this were not A1, if this was not airplane 1, if this was airplane 2, then what is happening in case of airplane 2? In the case of airplane 2, when the angle of attack is alpha c, then the moment coefficient is positive. Positive means pitch up. Okay, so in case this is not airplane 1 we are talking about, this is airplane 2, then when the angle of attack is alpha c, because of positive which will be generated, the aircraft will be rotated more upward. Okay, so from alpha c, it will pitch more upward. Okay, so the angle of attack will increase more. So this will not be statically stable. So what we have found here is when the angle of attack increases from alpha b to alpha c, this airplane 1 is statically stable, whereas airplane 2 is not statically stable, right? Statically unstable. Okay, simply because at this new angle of attack alpha c, the moment coefficient is positive for this airplane. So positive means when the angle of attack becomes alpha c, the aircraft will be pitched more up. Okay, so the angle of attack will be increased more. So it will continue to increase the angle of attack, and this aircraft will just, at a very high angle of attack, it will stall. So that's not good. Now let's consider another case. In the second case, let's say, again we have our aircraft which is flying at an angle of attack of alpha b, and now let's say the gust of wind came from the upper direction and it pushed the aircraft downward, it rotated, and the angle of attack decreased. So let's say now the aircraft is like this, where this is the new angle of attack. So let's call that A, alpha A. So what will happen now? Because of the gust of wind, the state of equilibrium has been disturbed. The angle of attack has changed from alpha B to alpha A. How will airplane A respond? How will airplane 2 respond? So there are airplane 1 and airplane 2. So let's first try to understand how airplane 1 will respond in this situation. Okay, so airplane 1. So we have to refer to this black line, black plot. When the angle of attack is alpha A, for airplane 1, a positive moment will be generated. Okay, because this is positive. So positive moment will, what will it do? It will pitch the aircraft higher, right? It will try to increase the angle of attack. So from alpha A, because of the positive moment, the aircraft will again try to rotate back to its equilibrium position, or it will try to rotate back to a higher angle of attack. Okay, which means it is stable. Now let's try to understand how airplane 2 will behave. In the case of airplane 2, at this new angle of attack alpha A, a negative moment will be generated. Right, negative moment will try to pitch the aircraft downward. It will try to rotate it downward. So from alpha A, the angle of attack will decrease more. So maybe because of the moment which is generated, the aircraft will become like this. Okay, so this gust of wind changed the angle of attack to alpha A, and because of the positive moment which is generated, the negative moment which is generated in the case of airplane 2, the angle of attack will decrease more. Okay, so or the aircraft will be it will try to rotate downward. So again, from this example, we conclude that this airplane 2 is not stable. Okay, statically unstable. So what we can infer from this explanation is that if Cm versus alpha is negatively sloped, then the aircraft is statically stable. If Cm versus alpha is positively sloped, then the aircraft is unstable, statically unstable. So the conclusion from this sort of analysis is, for static stability, the slope of moment coefficient as function of angle of attack should be less than 0. That is the conclusion from this discussion. Now in this course, because there are so many derivatives, there are so many slopes which will have to be written, it becomes very soon very tedious to keep writing d something over d something, so for that reason there is also a shorthand notation to write the derivatives. Like this dCm d alpha is written as Cm alpha. Okay, this is a shorthand notation for dCm d alpha. So you have to get used to this. Okay, so as the equations will become longer, instead of writing dCm d alpha, I will be writing Cm alpha, and you should understand that Cm alpha is the same thing as dCm d alpha. Okay, so this is very important. Why is it important? From the application point of view, if I give you a problem statement and if I ask you whether this aircraft is stable or unstable, how will you answer? You will calculate this dCm d alpha. If you find that it is negative, your conclusion will be that the aircraft is statically stable. If you find that dCm d alpha is positive, then you will conclude that it is statically unstable. Okay, so this is something which will be useful in solving problems as well. Okay. So the question is this enough? I mean, is there something more that we would like to do in terms of this Cm versus alpha? So this satisfies dCm d alpha is less than 0. This also satisfies the stability criteria. So which one do we prefer is the question. Okay, so do we prefer option A? Let's call this option A. Let's call this option B. Which one do we prefer? Now let's see. In case of option A, at the trim point, we have a positive angle of attack. Right, so note that the trimmed alpha is positive. In option B, trimmed angle of attack is negative. Which one is better? If you think of the CL versus alpha plot, from this plot, which we have already discussed in our previous courses, you can notice that when the angle of attack is positive, we get a very high lift coefficient, correct? When the angle of attack is negative, we get a low lift coefficient. See, in addition to being statically stable, it is also desirable to have a high value of lift. So although both A and B are equilibrium conditions, both option A plot and option B plot are equally stable, but at point A we get a higher value of the lift coefficient, and this is better than point B where the value of lift coefficient is small. At point A the aircraft will be flying like this. If we choose this one, in the equilibrium condition the aircraft will be flying like this, right? And this may be more preferable. But the main reason is the comparison between the value of lift coefficient, because at a higher angle of attack the value of lift coefficient is high. Okay, so what we conclude from here is, when we design the aircraft, of course we want the slope of the moment coefficient to be less than 0, But in addition to that, we also want this intercept to be positive. See, for the option A plot, the intercept is positive. For option B plot, the intercept is negative, right? Intercept means this value. So the second condition I would add is CM0 should be greater than 0. But this is more from the lift point of view rather than the stability point of view. Consider this dCm d alpha. This can be written as dCm dCl dCl d alpha, correct? That's just the chain rule, right? So the trend that you will get for Cm versus alpha will be the same as the trend you will get for Cm versus Cl. So if this is my Cm versus alpha, then Cm versus Cl will also look the same. I mean, it will. So if this is Cm versus alpha is negative, then Cl will also be. This alpha will have a positive slope, then Cm versus Cl will also have a positive slope, because this Cl versus alpha has a positive slope and it is a constant. Okay, it is a constant no matter where you measure it. The slope of Cl versus alpha does not change. So instead of writing dCm d alpha is less than 0, you could also say that for static stability, dCm dCl is less than 0. Means the same thing. Okay, these two statements are same. They are equivalent to one another. When you solve a problem, if you do not have the information to calculate the derivative of moment coefficient with respect to the angle of attack, you could also calculate the derivative of moment coefficient with respect to the lift coefficient. And if you find that to be less than 0, then also you could conclude that the aircraft is statically stable. Each component of the aircraft affects its stability characteristics. The aircraft as a whole has a stability characteristic, but that can be determined by adding the contributions from each component. So you could find this dCm d alpha of the wing. You could find this dCm d alpha of the tail, dCm d alpha of the fuselage, and let's say there are engines as well. Okay, dCm d alpha from the engines, and this is equal to dCm d alpha of the entire aircraft. So the next topic or subtopic is to look at these components individually. So we want to calculate this, the wing contribution. We want to calculate the tail contribution, fuselage contribution, and the engine contribution. And then you will obtain the value of the total moment slope. And in this process, you may realize that the wing contribution may actually be positive. But if other things are negative, then overall there will be a negative value for the moment slope, and overall the aircraft could be stable. We're going to start with the wing contribution to static stability. Consider the fuselage reference line, FSR. This is called the fuselage reference line. So this line lies in the plane of symmetry of the fuselage. So you can think of this as an axis or the line of symmetry. Okay, so when you have this aircraft, so the fuselage reference line could be somewhere here. So it is in the plane of symmetry, and it's at some height from the from the bottom of the aircraft. Okay, now the wing could be mounted at an angle, right? So let's say this is the wing of the aircraft, and this is the chord. Okay, now the chord can change from tip to the root, right? So if it is a tapered wing, then chord can vary from tip to the root, but we can calculate the average. Okay, so this average is called the wing mean chord. So wing mean chord, and it is represented by C bar. Okay, so it is the average chord. So this line here that I've drawn, the blue line, it represents the wing mean chord. So you are looking at the aircraft from the wingtip. Okay, so you're looking at it from here, and you only see the projection of the chord. Now, the angle at which this mean chord is set with respect to the fuselage reference line, this angle is written as IW. Okay, so IW is the angle the wing chord line, wing makes with the fuselage reference line. Sorry, this is not FSR, it's FRL, right? Fuselage reference line. Now let's imagine that the aircraft is descending. So the blue arrow I sketched indicates the flight path. Then in that case, the angle of attack would be the angle between this relative wind and the chord line. This is my angle of attack, but I'm going to put a W as a subscript because now we want to make distinctions between the different components. So we are talking about the wing, so I have alpha W there. Okay, and the angle that the relative wind makes with the fuselage reference line, change the ink here, this angle will be denoted by alpha FRL. So that is the angle that the fuselage reference line makes with the relative wind. Now, a few other things I want to label. Let's say that the resultant aerodynamic force acts at this point on the chord line. Okay, so the point where this resultant aerodynamic force acts is called the aerodynamic center, right? And the drag force is going to be in the same direction as the relative wind. Okay, so when I sketch a vector representing the drag on the wing, that should be parallel to the relative wind. So the lift will be normal to that. So this vector here represents the lift on the wing. The resultant aerodynamic force also creates a moment about the aerodynamic center. So I'm also going to label that. So this is the moment about the aerodynamic center of the wing. And let's imagine that the center of gravity of this aircraft is somewhere here. This is the center of gravity. And the vertical displacement of the center of gravity from the fuselage reference line, so this distance is labeled as ZCG. Okay, so ZCG is the vertical displacement of the center of gravity. All right, now there are a few other things which we need to label here. So the distance from the leading edge of the wing to the aerodynamic center of the wing, this is labeled as XAC, and the distance from the leading edge of the wing, okay, against this line to the center of gravity, this is labeled as XCG. And to calculate the stability characteristics, XCG and XAC are very important. Okay, we have to know the values of XAC and XCG, or at least their difference, in order to calculate the moment slope. So before we can calculate this moment slope, dCm d alpha or dCm dCl, we need to first obtain an expression for Cm. We need to obtain an equation for Cm. To obtain an equation for Cm, first we need to obtain an equation for moment. So the next step in this process is to calculate the moment about the center of gravity. So we will be adding the contributions of the drag force, the lift force, and this moment about the aerodynamic center in order to calculate the moment about this center of gravity.